Welcome. We are in the third lecture of this module of case study of design of a gas absorber and economic decision making for the design. We have already seen the synthesis of flow sheet, then we saw the process alternatives, then in the last lecture we tried to design the main unit of the absorber, that is the absorber column itself, using some simplified equation. We started with Kremser's equation and then we tried to simplify it, and then we saw that we lose very little of accuracy, but we simplify calculations to a great deal by making modifications of the Kremser's equation. That kind of approach can be adopted to all design processes. So, we shall see again some other case studies later. In this lecture, we will try to focus on the rules of thumb of the process design. While designing the gas absorber, we made use of two thumb rules, that is a recovery of 99% and above for acetone, and second was the liquid flow rate to the absorber, that is L by mg equal to 1.4. These were the two thumb rules that we used. Now, how these thumb rules have come? Thumb rules are usually developed by experienced designers. So, suppose there is a designer who has already designed 10, 15, 20 absorbers and has found that the most optimum design was at L by mg equal to 1.4 or close to 1.4 and for solute recovery of higher than 99%, then that is how he started with that experience for the next absorber. Okay. But now several softwares are available in which you can do very large parameter study, and therefore, you can easily develop rules of thumb using these detailed simulations. Okay. However, in some cases optimization calculations might be very sensitive to changes in design and cost parameters. Like whatever design parameter that we have used, if the cost of operation or the capital cost is very sensitive, then the rule of thumb may not be that applicable. However, if the design and cost equations are relatively insensitive, we should be able to simplify equations as we did in the Kremser's equation case, and then we can develop some rules of thumb. Now, use of order of magnitude arguments to simplify a problem should be able to give us some rules of thumb that we have seen. Okay. Like for example, in distillation column, there is a rule of thumb that reflux ratio should be 1.2 times the minimum reflux ratio. Okay. This again has come out of order of magnitude calculations. Okay. The assumptions used in the analysis will clearly indicate the potential limitations of the rules of thumb. Now, what we will do is that we will see as what is the basis for this particular thumb rule that we have used in the design of absorber. As I just mentioned, we have used two thumb rules, recovery of 99% or more solute and L by mg equal to 1.4. Now, let us see the validity of these thumb rules, as what is the basis for this thumb rule. I would like to specifically mention that Kremser equation is mainly applicable for dilutes and isothermal system, where both operating line and equilibrium line are, both operating curve and equilibrium curve are essentially straight lines. Okay. That is when the system is dilute or the concentration of solution is dilute and the operation is isothermal. Let us see how we have come at L by mg equal to 1.4 thumb rule. I would like to note the point I just mentioned. Kremser's equation is applicable for dilute and isothermal systems. Let us see a plot of this Kremser's equation. What you see on the screen now is a plot of the Kremser's equation. On the x axis you have L by mg, on the y axis you have the parameter y out minus mx in divided by y in minus mx in, which is essentially the percentage recovery. Okay. Now, we want to recover as much as acetone as possible. Okay. Now, let us say that we pick up L by mg equal to 1, which is particular basically this line which I am now showing. Okay, L by mg equal to 1. Now, you can see that we cannot get close to the complete recovery, that is y out minus mx in divided by y in minus mx in equal to 1, even with infinite number of plates. What you see here is the parameter is number of plates and the percentage recovery for L by mg equal to 1.4, and you can see here that even with the infinite number of plates, which is this particular tangent, okay, if L by mg equal to 1, I cannot get complete recovery. Okay. Now, complete recovery is desirable when the solute is very valuable, or if the solute is highly toxic, for example, hydrogen cyanide. Okay. So, in these two cases, we would like to have as high recovery as possible. Okay. And therefore, L by mg equal to 1 or less than 1 is never going to give us that kind of recovery, desired recovery. Now, let us say that we double the ratio L by mg equal to 2. Now, here we see that follow this line which I am showing now. Okay, L by mg equal to 1, we see that we get very large recovery, okay, or almost complete recovery within just 5 or 6 plates. Okay. However, the solvent flow rate in such case will be very high for a given gas flow rate. Okay. Now, if solvent flow rate is high, then the load on distillation column will increase. Remember that when we are optimizing a flow sheet, our attempt should be optimize the complete flow sheet and not a particular equipment. Now, equipment are interconnected, so optimization of one equipment may de-optimize another equipment. So, we have to have a sort of a global view of the flow sheet while optimizing the flow sheet. Therefore, if I use L by mg equal to 2, I know that I am going to get very high recovery or almost complete recovery in just 5 to 6 plates. That means a very short column whose cost will be very small. I mean, when we talk of investment of crores of rupees for a process plant, if the absorber is costing me few thousand rupees, then it is almost negligible. Okay. However, I have to take care of the distillation column that is in the line with absorber. Okay. I am going to recover the solute from the solvent of the absorber using the distillation column, and L by mg equal to 2 is going to create intensive load on that column. I will have high vapor flow rate, high reboiler heat load. Okay. So, that will make my distillation column highly expensive. Okay. Therefore, we have to find something in between. We have to go for a value which is between 1 and 2. Okay. That could be our optimum value. Okay. Now, if I put L by mg equal to 1.5, which is exactly halfway, okay, then again if you go back to the plot, you will see 1.5 is somewhere here. Okay. You will see that you are going to get almost complete recovery within about 16-17 plates. Okay. So, therefore, we have a trade off between decreasing the number of plates, okay, which will reduce the capital cost, and increase in the operating cost of the distillation column by putting liquid flow rate. Okay. However, distillation operation is energy intensive, therefore, we would like to have a slightly lesser liquid flow rate than L by mg equal to 1.5. Okay. Therefore, in order to optimize the operating and capital cost of both distillation column and absorber together, we choose a little less than 1.5 L by mg, that is could be 1.4. Okay. So, that point we note. L by mg equal to 1.5 gives almost complete recovery, in merely 15 plates. Okay. However, we have to trade off between capital cost and operating cost of both distillation column and absorber. If I put more liquid, the number of plates will go down, but the load on distillation column goes up, and distillation being an energy intensive operation, we choose to have a little less than optimum liquid flow rate for absorber, so as to reach optimum operating cost for distillation column, and therefore, we choose L by mg equal to 1.4. So, this is a common rule of thumb for the absorber design. Okay. Now, the second thumb rule that we have used is fractional recovery. Of solute greater than 99%. This is second thumb rule that we have used. Okay. Now, again here there is a trade off. If solvent flow rate is fixed, we can increase the solute recovery by adding more plates in the column. If solute recovery increases, then solute loss through exiting gas reduces. In previous lecture, we have already estimated the loss of acetone through exiting air to be about worth $6,000. So, that point I repeat again, we estimated loss of acetone through air to be worth $6,600 annually. So, if the solute recovery increases, obviously this loss decreases. Okay. So, the trade off is like increasing the capital cost by addition of plates and decreasing the cost of solute loss. We will try to form a sort of an objective function that will give us the total cost. One of this cost, like capital cost, is a single time cost, okay, and the other cost is recurring cost. So, how do we bring the two cost on the same platform? In the previous module of project economics, we have already seen several such methods which bring the two costs on same platform. One of them was the use of capital charge factor, or what we had abbreviated as CCF. Okay. So, if you multiply the capital cost by CCF, gives the annualized capital cost. And we shall use exactly the same technique for formation of the objective function. So, let us say that the total annualized cost that we denote by TSE, units of dollar per year, is equal to the cost of solute CS dollar per mole into the loss of solute G into Y out, that is mole per hour, into the total number of hours of operation per year 8150. Okay. So, this is what the total loss is of the solute, okay. And then the cost of the plate, okay, but it is an annualized cost. So, dollar per plate per year into the number of plates n is the annualized capital cost. So, this is the objective function that we are going to optimize. This objective function gives the total annualized cost in terms of the fractional recovery. For n, we substitute 6 into log y in by y out minus 2, the expression that we derived in previous lecture, that is simplified Crumbs equation. Okay. And then we write total annualized cost as 8150 into CS cost of solute G Y in, G is the molar flow rate of carrier gas, okay, Y in. Now, in the original objective function, the loss of solute was written as G into Y out, which we rewrite as G into Y in into Y out by Y in, okay, and the annualized cost of plates. And now we differentiate this with respect to the recovery Y out by Y in and then equate it to 0. So, what we see is 8150 into CS into G into Y in minus 6 into Cn divided by Y out by Y in. And then if we rearrange, we get the optimum fractional recovery at which the total annualized cost is minimum. That turns out to be 6 into Cn divided by 8150 into Cs into G into Y in. We put some typical values in this expression. Let us say the cost of solute is $15.5 per mole. The total flow rate of solute into the absorber G into Y in is 10 mole per hour. The cost of plate is $2250 per plate, but annualized cost is this divided by 3. Now, why 3? Because we have considered capital charge factor as 1 by 3. Now, how capital charge factor is equal to 1 by 3? This derivation has already been covered in the module of project economics. So, I would request you to revise it. Okay. So, $2250 by, so that comes out to be something like $850 per year. So, this is annualized cost of the plate. If you put these numbers and then try to calculate the optimum fractional recovery, you will see that Y out by Y in is 0.004, which essentially means or implies that 99.6% recovery, and this justifies our thumb rule. Let us see how sensitive is this particular fractional recovery to the cost. Sensitivity analysis. Suppose if any of the numbers that is on right hand side, any of the cost number that is on right hand side doubles, then also we are close to 0.01, which means 99% recovery. So, try substituting instead of 850 here maybe 1000, or for 15.5 you substitute 20 or 25, whatever number. No matter which number, cost number that you double, okay, you are very close to 99%, okay, or the value of y out by y in comes out to be 0.01. Okay. This means that the optimum values of parameter design parameters are relatively insensitive to cost. Or in other words, the total cost of operation of the process is relatively insensitive to the design parameter. Okay. And this is a characteristic of a large number of design problems, that solutions are often very insensitive to the physical property data or the functional form of design equation or the design parameters such as heat transfer coefficient, cost data, etc. Okay. Therefore, good engineering parameters, good engineering judgment requires that we obtain some idea of the sensitivity of the solution before we go further with the analysis, with the design. Okay. So, that point we note, that good engineering judgment requires that we obtain some idea or a rough idea of the sensitivity of solution or of design to the design parameters. Before we go for more rigorous design. That is, in other words, we spend as little time as possible to get the answer for the design, and we want that answer to have close enough accuracy that the decision we are facing with. So, that is the discussion on the rules of thumb. Question comes as whether rules of thumb should always be applied or will there be any limitation, under what circumstances the rules of thumb may not be applicable. Okay. So, that point we will discuss now, limitations of rules of thumb. I would like to repeat one point that I have stated earlier, that Kremser equation is valid for a dilute system in which the absorber operation is nearly isothermal. That means a relatively small amount of solute is absorbed in a relatively large amount of solvent, so that the heat of dissolution that is liberated with the absorption of solute does not increase the temperature of the solvent significantly. Okay. This is possible only when the amount of solute that is dissolving is small. If the amount of solute is large, then the temperature of solvent increases as the liquid flows down the absorber, and then the equilibrium characteristics also change. In that case, the equilibrium curve is not likely to be a straight line as in case of Grimser's equation. So, that point we note that for concentrated mixtures, the equilibrium curve may not be a line. Okay. Now, how do we determine the minimum liquid that is required for a particular operation? You might recall these kind of graphs that you made in mass transfer 1. Suppose you have a counter current absorber where G is the gas that is going in, carrier gas, with mole fraction Y in of the solute. The same gas comes out with mole fraction Y out. The liquid that goes in is L with mole fraction of solute X in, and the liquid that comes out is again L with mole fraction X out. Okay. And then you have the equilibrium line as Y star equal to mx. Now, given that you have to reduce certain mole fraction of solute from Y in to Y out, you are supposed to calculate the minimum liquid requirement. So, what you do is essentially you try to get the 2 points Y in and Y out on the Y axis. From Y in you draw a straight line, okay, that cuts the equilibrium curve, and from this point you draw a line joining point Y out and X out. This point is X out, X in. We assume here that X in is 0. Now, the slope of this line will give you the minimum solvent that is required for absorption. Now, when you use minimum solvent, then you have a pinch at the bottom of the tower. That means, the outgoing liquid is always in equilibrium with the incoming gas. The point G in and Y, the point Y in and X out indicates the bottom of this particular absorber. You will always choose a liquid flow rate that is higher than the minimum, which gives the operating line, and then you would like to make out the number of plates or number of trays that are required for a particular operation. This is what procedure you have followed while determining the number of plates in case of dilute and isothermal systems. However, in case of concentrated system, the curve, the equilibrium curve itself will be either parabolic or the reverse. This kind of curve will be obtained if the absorption is favorable, which means the amount, the solute for soluble gas vapor, okay, soluble vapor, and this is for unfavorable. Okay. Now, in such cases, to have the same reduction of concentration of a particular solute, you will find the minimum liquid flow rate using this procedure, that you will draw a line, horizontal line, that will cut the equilibrium curve at point y in x out, and then you join the line. However, in case where the curve is not concave but convex, as I am showing now, the minimum liquid flow rate will be determined by the tangent to the curve from point y out. Okay. So, that point we note for concave equilibrium curve, the procedure for determining minimum liquid flow rate is same as for dilute system. Okay. However, the minimum flow rate or the optimum flow rate may not be equal to L by mg equal to 1.4. It could be relatively less because of the solubility of the particular solute. Okay. You may get optimum design at L by mg equal to less than 1.4 if the equilibrium is favorable, is concave. In case of convex equilibrium curve, okay, the reverse is true. Okay. In case of convex curve, the solute dissolution is not favorable. In case of convex equilibrium curve, the solute dissolution is not favorable, and the minimum liquid flow rate will be determined from the slope of the tangent drawn from the point y out. The slope will obviously be L by g minimum in both cases. Okay. Now, this L by g minimum may be much higher than 1.4, okay, because it has no relation whatsoever with L by mg equal to 1.4. Okay. The minimum flow rate itself, the minimum flow rate of liquid itself could be much higher than L by mg equal to 1.4. So, these are the rules, the limitations of rules of thumb. You cannot apply rules of thumb every time. You have to see the similarity of your system, the limitations of your system with the system for which the rule of thumb is derived, and if significant similarity exists, then you can adopt the rule of thumb for designing your own system. Okay. Now, how do we make our system behave close to ideal, or how do I make absorption column operate isothermally? If I look at the slope of the equilibrium curve m, which is gamma PV by PT, that is what we derived in previous lecture, we see that the slope of the equilibrium curve is basically dependent on two parameters, that is gamma activity coefficient and PV, the vapor pressure of solute at the temperature of operation. If I keep the temperature of operation constant, okay, then both gamma and PV are likely to be constant, and therefore, the equilibrium curve is likely to be a straight line for which I can apply the Kremser equation. Now, how do I make sure that my absorption column operates isothermally? Obviously, I will have to take care of the heat transfer, have proper heat transfer system so as to control the temperature rise. This could be like placing of cooling coils below the plate, or pump around cooling loops at the bottom, or 2-3 trays of the gas absorber. However, this needs structural changes in the equipment. If I have an absorber and if I want to put cooling coils below each plate, I will have to dismantle all the plates, then put the cooling coil, weld the cooling coil below, and then reassemble the column. Okay. So, this involves a significant structural change which has significant economic impact on the design. Okay. And thereafter, I will have to carry out optimization again. After I do structural changes. Therefore, another thumb rule that we can develop out of our own analysis for absorber is that avoid use of adiabatic absorber, or make your absorber isothermal, as much isothermal as possible. So, this was essentially the complete case study of economic decision making, or finding the optimum values of parameters for a particular process unit. Now, we shall see a small example, okay, of similar type, in which we will try to determine the optimum temperatures of the heat exchanger units. We shall see a small problem on optimization of a particular process unit, taking into account the total annualized cost, or let us say economic optimization of a process unit. What you see on the screen now is a heat recovery system. Waste heat stream enters a steam exchanger in which saturated water is fed and is converted into steam, okay, and then the waste heat stream further goes to a cooling water exchanger, where cooling water is used to cool this stream to 100 degrees Fahrenheit. So, it is a system of 2 consecutive heat exchangers. Okay. Now, I have given here all the parameters as you see on the screen. F is the flow rate of waste stream, that is 51,100 pound per hour. T in is the temperature of waste stream, that is 366 degrees Fahrenheit. Cp is the heat capacity of waste stream, that we assume to be 1 BTU per pound per degrees Fahrenheit. Ts is the saturation temperature of steam and temperature of water inlet to the steam exchanger, that is exactly same as 267 degrees Fahrenheit. So, there is only the phase change taking place in the steam exchanger with no superheating. Delta Hs is the heat of vaporization of steam, that is 933.7 pound per 933.7 BTU per pound. Then US is the overall heat transfer coefficient of steam exchanger, taken to be 20 BTU per hour per feet square per degrees Fahrenheit. UC is the overall heat exchanger overall heat transfer coefficient of cooling water exchanger, that is estimated as at 30 BTU per hour per feet square per degrees Fahrenheit. CA is the annualized cost of heat exchangers, okay, that is estimated at $11.38 per feet square per year. CW is the cost of cooling water, estimated at just above 7 cents, $0.074 per pound per hour per year. CS is the cost of steam, taken to be $21.22 pound per hour per year. WS is the steam flow rate in pound per hour. WC is the cooling water flow rate in pound per hour. T1 is the intermediate temperature of the waste stream. AS is the area of steam exchanger in feet square, and AC is the area of water exchanger or the subcooler in feet square. Okay. Now, what we have to find out is the optimum intermediate temperature T1, for which the total annualized cost of the unit is minimum. Now, how we can write the total annualized cost of the unit? Okay. It is the annualized cost of the first exchanger, steam exchanger, into the area of exchanger, then the annualized cost of the subcooler into the area of subcooler, then this is the annualized capital cost of the two exchangers, okay. Then the operating cost. CW is the cost of water into the water flow rate, and now since the steam is generated into the system, that is considered as an income from the system, the steam can be utilized elsewhere. So, the annual cost of steam we subtract from the total annualized cost. So, the objective function in the present case is this TAC that you see on the screen. Now, in the steam exchanger, the heat given up by waste stream is picked up by the rising stream or the water stream. Okay. We, for simplicity, we assume 100% efficiency. Okay. So, we can very quickly write the heat balance across the steam exchanger. F into Cp into T in minus T1 is the heat given up by waste stream, and that should be equal to US, the overall heat transfer coefficient, into the area into the LMTD that you see on the screen, and that heat is picked up by water, that is converted to steam. So, Ws into delta Hs. Okay. Then the next exchanger, here again F into Cp into T1 minus 100 is the heat given up by waste stream. The exit temperature of waste stream is taken to be 100 degrees Fahrenheit, and again in terms of LMTD and overall heat transfer coefficient, it should be UC into AC into T1 minus 120 minus T1 minus 90 is this, and then this is the heat absorbed by cooling water. The cooling water flow rate into the heat capacity into 120 minus 90, that is the temperature rise of cooling water. Okay. After having done the heat balances, as you see for both exchangers QS and QC, what we try to do is that we try to get values of the 4 design variables: the area of steam exchanger, area of subcooler, and the water flow rates in for both the systems in terms of the process parameters. We have rearranged the equations to get AS in terms of F, Cp, US, T in, Ts, T1 and Ts. Similarly, a similar expression for AC, the area of subcooler, and then the 2 flow rates. Wc is the water flow rate to subcooler, and Ws WC is the water flow rate to subcooler and WS is the water flow rate to steam exchanger. Now, having done this, we substitute these values in the total annualized cost, okay, and then we get an expression of our total annualized cost. Okay. Now, here all the parameters on the right hand side are given except the T1, okay, and that we treat as variable. So, optimum value of the intermediate temperature T1 for which the TSC of the heat recovery system will be minimum can be determined by taking partial derivative of the objective function TSC with respect to T1. Now, here we make a small approximation that we assume that T1 minus 100 is more or less same as T1 minus 130. Now, this is possible if T1 value is sufficiently high. Of course, this is an approximation to make objective function simpler, and with that approximation the modified objective function is Ca into F Cp divided by Uc. So, the intermediate bracket is now gone, okay, ln T1 minus 120 divided by 30, so on and so forth, and now we take the partial derivative and then obtain an expression minus Ca by Us into T1 minus Ts plus Ca divided by Uc into T1 minus 120 plus Cw divided by 30 plus Cs divided by delta Hs. And now, we substitute values of all the parameters, like Ca was 11.38, that we substitute here, Us was 20, Uc was 30, then Cw was 0.074 and Cs was 21.22, delta Hs was 933.7. Solution of this equation will give a quadratic in T1. Okay. Now, those minor calculation I leave to you, algebraic simplification, and then if you take the roots of the two equation, the two roots of that particular quadratic equation, you will find that the roots are T1 equal to 106.8 and 287.7 degrees Fahrenheit. Out of these two roots, the 106.8 is physically not meaningful, because the exiting cooling water from that particular exchanger is at 120 degrees Fahrenheit. So, the inlet temperature of hot stream cannot be lesser than that. So, we discard this value 106.8 and then we choose the value of 287.7 degrees Fahrenheit. So, the total annualized cost of the heat exchanger unit will be optimum at an intermediate temperature of 287.7 degrees Fahrenheit.